This week, what's due on Sunday is lessons 8.04, which is over density, and then 8.05, which is over three-dimensional shapes. So that's a pretty cool one. I like the three-dimensional shapes lesson every year. That's always gets into some good graphics that we get to play with and look at. Just some things to kind of consider. I am recording this so we can put this on Google Classroom for you to look at later. If you read through the lesson later and don't remember some of this or want to see the graphics again, I'll have that available. But I'm going to kind of review this week's lessons. This in no way replaces the lesson. You still need to read through there because it goes through a lot more detail. I'm giving you kind of a nice summary of what we're looking at. So mine kind of adds on to it because I'm adding some more visuals and stuff to kind of help you understand what the lesson is telling you. So that's what I'm doing today with that. As far as lesson 8.04, pretty simple. 8.04 is just over density. If you add to your notes, I'm going to show you. Let me turn on my Ladybug. And so we had our notes. You know, I had made notes for earlier 8.01, 8.02 notes, because remember, you can always use your notes from the tests, quizzes, everything. So all I have added for 8.04 is just this one formula. If you look at the review at the end of the lesson, that's all it gives you: density, mass, volume, and it gives you a definition of what density, mass, and volume are, which you could add that to your notes. But this is it: density equals mass divided by volume. That is the entire 8.04 lesson. So I'm going to show you a problem or two that you would have with the 8.04 assignment. So showing you what we added to our notes there. Let's go over a representative problem that they give you to say, okay, so the problem says you've got 12 fish, and they are in, all right, 12 fish, and they're in a tank that holds 45 cubic feet of water. Now, we generally think in gallons, but it's giving us dimensions, cubic feet of water, and it wants to know the density. Well, the fish, the 12 fish, this would be the mass. And how much water it holds, that's the volume of the tank, right? So since density equals mass divided by volume, the density equals 12 divided by 45, which we can throw out our calculator and calculate. 12 divided by 45 is 0.26 repeating. So we'll round that to 27. So 0.27 is the density of the fish in our fish tank. So basically that means for every 1 cubic foot of water, there is about a fourth of a fish, 0.27 of a fish for every cubic feet, which means each fish has almost 4 cubic feet of water. So it has a lot of room. There's not very many fish in this tank because it's about 1/4 of a fish per cubic foot. So that's not bad. So the density is pretty simple to work with. As long as you have this formula, density equals mass divided by volume, it's really easy to calculate density. Now, they may give you the density. They say, okay, we have a density of 1765 of helium in this helium balloon. That's the density. We have that many kilograms per cubic meter. All right, 0.1265 is the density. And it says if this balloon holds 2,000 cubic meters of helium or air, what is the density of helium in there? How much helium is in there? Well, they gave us the density this time. So that's the 0.1765. It says this is how much it holds. So that's the volume. So we're trying to find the mass. It tells us the density is 0.1765. Tells us the volume, does not tell the mass. So the mass would be, since the mass is divided by 2,000, we need to multiply by 2,000 to get mass by itself. Got to do that to both sides. So the mass equals 2,000 times the 0.1765 density. So 353. And it would be kilograms because this is kilograms per meter was the density per meter cubed. And so this is, since this is meters cubed, that would be kilograms, right? Kilograms per meters cubed. That's why that is the units for the density. It's kilograms per meter cubed. So the mass is 353. There's 353 kilograms of helium in this balloon. So that's all that 804 is using our density formula and manipulating it to find either the D, M, or the V, right? The density, the mass, or the volume. You just have to rearrange the equation for whatever information is given to you for what you need. So now I want to look at 8.05. That's the fun one, 3D shapes. And so let me show you some of the things to do. There's three different things we're looking at in here. One of them is a cross section. And that's where you have a shape and you're going to take a slice of it out and look at that slice. All right. Just taking a slice out of a shape and saying, what does that look like? Like if I have this drink and I take a horizontal slice, what does that look like? What would that shape be that I pull out of the middle of this cup? Also, what we will look at is having a shape and rotating it around an axis. If we have a two-dimensional shape and we rotate it around an axis, what kind of three-dimensional figure does it create? And then the other thing is a net drawing. And in net in geometry, we talk about if we have a cube and we unfold it to where it's flat like a piece of paper, what does that look like? Well, a cube would be, you know, 4 strips with the 2 side strips that make up the end. So 4 squares that would all fold together, and then the 2 side squares that fold up. We're going to look at the shapes in this unit. We're not using a cube, but let me show you. We're going to start with looking at the sections. If we take a cross section of a sphere. All right, so here's a sphere, and this blue plane, I'm going to make it a little bigger. This blue plane is considered like taking a blade and just sliding it right through the middle of the sphere. What kind of shape does that cut? So we can turn it and look. So it makes a circle right there. We're cutting a circle out of the sphere, and the size of the circle is just going to depend on how high or low it is. You know, get towards one of the ends, the circle gets smaller because we are near the bottom or top of the sphere. And with a sphere, even if we tilt it, right, if we tilt it at a diagonal, we're still getting a circle. If we go straight up and down with it, it's still a circle. No matter how we cut a sphere, at what angle, what diagonal, whether it's parallel to the ground or whether it's perpendicular, it's always going to be a circle. A sphere is a pretty easy one to understand cutting out of there. So let's look at something different than a sphere. We will also look at a cone. Okay, so let's look at a cone here. So here's a cone, and if we do a parallel, we talk parallel to the ground, parallel to the base, parallel cross section, it's going to make a circle, right? Because the base is a circle. It could be a big circle if it's parallel and very close to the bottom. It could be a very small circle if it's up close to the top. But a cone makes a circle also. But what about if we turn that at a diagonal? If we start tilting that, there, tilting that. Now what shape is that? I'm going to raise it up a little higher so I can tilt it more. Is that still a circle? Let's turn and look. See, that's more of an ellipse. It's an ellipse. It's not round as far as perfectly round as a circle. It's round as an oval. It's an ellipse because it's a diagonal piece that is not as wide as it is tall. But what if we continue and we take it all the way to the top? Oh, look at that cross section. If we do a perpendicular to the ground, if we do a vertical cross section, it makes a perfect triangle. It's an isosceles. The 2 sides would be the same length. The diameter of it just depends. If this diameter is the same as the height, it would be an equilateral triangle, but that's not usually the case. So it just depends on how wide the base of the cone is. But it is isosceles. Those 2 sides would be the same. But it makes a triangle when we take a perpendicular or vertical cross section of a cone. So nice visual. We tilt it. We get a parabola for a little while to get to the sides. Then we go to the ellipse and then back to the circle. So that is the 3 that we're looking at is the circle for parallel, the ellipse for a diagonal, and the triangle for a vertical slice. All right, enough playing with the cone. Let's move on to a cylinder. All right, so a cylinder, a cup, a can, right? Again, it's a circle. It's going to be the same size. Doesn't matter where we take this parallel slice because the cylinder is the same from top to bottom. But what about the diagonal of this? Let's tilt that at a diagonal. Let's turn that and take a look at that. That is also an ellipse. Also an ellipse. And when we do a diagonal section of a cylinder. But what about top to bottom? What about when it's straight up and down? What shape do you think it's going to be? Think about that. Somebody take a guess. What do you think? Put something in the chat. What shape do you think that'll be when we slice it straight up and down, perpendicular to the base? Any thoughts? Any thoughts? Got an idea? All right, here I go. I'm going to do it. Oh, did you predict that? Makes a rectangle. A rectangle. And again, if the height is the same as the diameter, it would be a square, but a square is also a rectangle. So it will make a rectangle when you take a perfect up and down cross section from a cylinder. We end up with a rectangle. So the three shapes we look at for the cylinder is we have a rectangle, or if we just do the diagonal, we have the ellipse, or we have the circle. All right, that's the shapes that we're looking at with the cylinder. I have one more, is the pyramid. Now, our text looks at a square pyramid. This is just a rectangular pyramid because the base is a rectangle, but a square is a rectangle again. So the same principles apply to that. So the cross section of this is going to be the same as the base. If it's a square base, that's going to be a square. Now, this is rectangular base. So this is a rectangle. And just the size of it depends on how close to the bottom or the top that you happen to be, right? All right, let's look at a diagonal. Let's go and raise up a little bit more, make it more extremely diagonal. All right, can you tell what shape to this? I'm going to turn it. Look at there, it's a trapezoid. It's a trapezoid. When we do a diagonal cross section of a square pyramid or a rectangular pyramid, you end up with a trapezoid. So that is unexpected, right? But it's perfectly horizontal, parallel top and bottom, but the top is much less wide. So you end up with a trapezoid. And straight up and down, you can probably guess the straight up and down. Oh, let me move that to the middle. So it's all not in the middle exactly. There we go. There's the middle. And we do end up with that same triangular shape. Triangular shape. And if we rotate around the other way, you know, it's still triangular shape. As long as it's straight up and down to the top, it doesn't matter if I rotate that slice. It's making a triangle any way I rotate that. As long as it goes through the tip top apex of the pyramid. So that is the slices of a square pyramid would be the triangle, the trapezoid, and the square, or the rectangle in this case for this illustration. All right, what else do we look at in this? We're going to look at net drawings. And what a net drawing is, if I gave you a piece of paper and I said, I want you to create a cone. I want you to cut out the shape of a cone that you can fold together and tape it, and it would be a cone. So what shape would you need to cut out, draw on your paper in order to fold it to be a cone when you're done? All right, let's see. I'm going to take this cone apart so we can look at it. See, as I move this, it takes that cone apart and makes it a flat piece of paper. That's it right there. Look at that. That is the shape you would need to make your paper. If you make your paper that shape, you'd barely connect the little circle, connect the circle with this kind of a fan shape, right? All those fans you open up and kind of, when you get too hot, you fan yourself with that. So I'll make that bigger on there. So as we close that back up, wraps right around and makes our cone again. Open and close. It is that shape. Flat, two-dimensional, folded up, three-dimensional. And you notice the length of this fan around that curve is the same as the circumference of the circle because it all fits perfectly together. All right, let's look at a different shape. All right, let's look at a cylinder. All right, so if we take the cylinder part, and I said, all right, I want you to make a cylinder now on your piece of paper. So draw the shape and cut it out. Let's take it apart, see what the cylinder is going to look like. Boom, there you go. It is a rectangle with two identical circles at the top and the bottom. It is a rectangle. And as we fold that rectangle back up, it makes our cylinder. But it is a rectangle with two circles. And the length of that rectangle is exactly the same as the circumference of the circles. Because when we fold it all together, it has to make exactly the same circumference as that circle did. So you can see that as we take it apart. It is exactly the same. But that is the shape you need right there to make a cylinder. All right, let's move on. I'll stop that. Let's move on to another one. And let's take apart a square pyramid. This is the square pyramid we've been looking at. What is that going to look like if we take this apart to where it's just a flat two-dimensional shape you can cut out of paper? Here we go. Let's open up our pyramid. And as we open it up, that's it right there on the left. It's a square with four identical triangles around it. They're isosceles. The two sides are exactly the same length. Two sides are the same length. As I fold it back up, and then you can fold it and tape it. You can fold it and tape it and make a pyramid of it if you make it that shape on your paper. All right. I have another one, but I couldn't find a moving graphic for it. But for the sphere, if you take apart the sphere in the same way, it would be like all these surfboard looking shapes down here. If you took a piece of paper and made that, you would be able to fold it and tape it together to be a perfect sphere. But that's what a sphere looks like when it's disassembled and made flat as a two-dimensional shape. So I wish I could find a nice visual moving graphic that we could do that, but I haven't been able to find one. All right, here's the last thing we're going to look at. If we have a two-dimensional shape and we rotate it around an axis, what shape will that make? Right here we have a right triangle, right? A right triangle. And if we have the right triangle right here on the y-axis and we rotate it around the y-axis, it's going to create a three-dimensional shape. All right, give that a thought. Think about that. Think about what's that going to look like? Get that in your head. What is that going to be if I take that right triangle and I rotate it around the y-axis? You got your guess. You got your thought in your head what that's going to be. Here you go. I'm going to start rotating it. I'm going to turn this where I can kind of get a better look at it. So as it rotates around, say we're rotating around the y-axis. There it is. Look at that. It makes a cone. As it rotates around, it makes a cone. So we can look and see the bottom of it, top of the cone. But that is a right triangle rotated around the y-axis. Makes this nice cone. All right, let's look at another one. We got two more. There we go. If we rotate, I'm going to make this one bigger. I forgot to do it in the other. If we make this bigger, this is a rectangle. Now, if we take a rectangle, rotate it around the y-axis, what shape we're going to have now. All right, get your guess in your head here. Get ready. I'm going to rotate it. Again, I want to kind of turn it. We get a good three-dimensional look at it. Okay, see that? Rotating it. Whoa, there we go. We'll make us a cylinder. There you go. A rectangle is going to make a cylinder. As we rotate that around, it fills in. It's going to be the same diameter from top to bottom because the rectangle is the same width from one side to the other, all the way from the top to the bottom. And we make a cylinder. So there it is, a nice cylinder as we rotate that around. Fun toys to play with here. All right, I have one last shape that we're going to look at, rotations. And this is all the 8.05 is dealing with these. It's asking you if we did a perpendicular slice out of this shape, what shape would you create? If we rotated this around an axis, what would you end up with? That's the kind of things we're looking at in this unit. Our last one is rotating a semicircle. So we got the semicircle. Right now it's kind of lying down. See, it's just a semicircle over there, and I'm gonna line it up so we can see as we rotate it. What is this going to be? Okay, got it. Ready to rotate. I'm gonna make it bigger. I didn't make it much bigger. Here we go. We're gonna rotate it. There it is, coming up. Yeah, that's it. It makes a blue Pac-Man. See, no, it's a sphere. I just didn't rotate it all the way. There you go. Rotate it all the way. It makes a sphere. It makes a ball. Makes a globe. It makes a sphere. And so we can see that as we rotate. Oh, we're on the back side of it now. So as we rotate that around, that semicircle becomes a sphere. So there you go. The mighty semicircle becomes a blue Pac-Man. Chompa, 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 chompa. All right, that is pretty much the entire 8.05 and 8.04. 8.04, it was just the density equals mass divided by volume, and 8.05 is these shapes. Now, what did that do for my notes? Let me show you my notes again. Again, remember, you can always use your notes on the tests. And so take good notes, and the end of each lesson gives you notes, gives you a review summary of that lesson. And that's a great thing to make your notes off of because it's got all of the new material you learned. So this was the notes I had for 801 and 802. 803 was the quiz. This was 804. And then 805, I need to make an entire page because we just looked at a lot with all these shapes. So I made an entire page and I typed it so I could read it all and fit a lot on there. So I went to the summary of 805 and it had all of this information. All of this information was in the summary of 805. So I copied and pasted it into my document. I said, okay, so a cylinder, if I take a parallel cross section of a cylinder, it makes a circle. If I make a perpendicular, it makes a rectangle, or a diagonal one makes an ellipse, right? That's the three things we looked at on the screen. And then I went into the internet and I typed cross section of a cylinder and found an image to go with it. Cross section of a cone, found an image to go with it. Cross section of a sphere, and put that in my notes. So this shows a parallel cross section and it made a circle. This one showed a diagonal, it made an ellipse, and this is the perpendicular and it made the rectangle. So a little easier to see on this. I found a better picture for the cone than I did the cylinder. You can see the triangle real nicely with the perpendicular cross section. And we have the ellipse and the circle. The sphere, remember, it doesn't matter which way we slice the sphere, we get a circle out of that. The square pyramid, there's the triangle shape, the square shape, the trapezoid, depending on how we slice that up. And then this was the net drawings. When we take apart this square pyramid, we end up with that shape. Take apart a cone, we end up with that shape. Take apart a cylinder, we end up with that. And that was the sphere, which I just took from that one website there, that sphere picture right there. And so this talks about in words what this shows you as a picture. And then the last thing is the rotations, and like the questions on the assignment, it'll ask you what shape could you rotate and create a cylinder? Rotate around an axis. Well, I look at my notes, I say, well, let's see, it says when a rectangle is rotated about an axis, it creates a cylinder. So I would type rectangle in. When a right triangle is rotated, it creates a cone. When a semicircle with a hyphen, semicircle creates a sphere. So just having those in my notes gives me everything I need for the test, all right, for the assignment and for the quizzes and the tests. I looked at ahead. We've got after spring break. This is the last thing until spring break, right? So you want to get caught up on all your work. But after spring break, we'll come back and we'll have like an assignment we do using this information, right? To use some of these volumes and all of this. And we'll do, there's like you got to do it all on paper, this whole assignment, and turn it in. Nothing new, not learning anything new on that. And then we have the practice test. And then we have the test like the second week after spring break. So having all of that means we've learned everything for this unit before spring break. So all we're doing after spring break is using an assignment to use these things, get us thinking again, taking the practice test. That'll be after spring break. Then the second week, we'll take the test. So these are all the notes I'm going to need because we're not learning anything else new. So if you have your note sheets down and you have all this kind of information, the test ought to get really easy. It's just as long as you know how to use these and you know what to put into what formula, how to rearrange the formula when needed, it gets pretty easy. And then, of course, the cross sections, Some of that you may be able to visualize and not need the note, but it's good to have the note just in case. If you're like perpendicular, oh, which way was that? And I can look at my note. Oh yeah, the perpendicular. That was the up and down triangle with the cone. So that is our review for the week for what this week's assignments are. So if you have over 70% and you would like to leave class, you are certainly free to do that. This is certainly optional, and I'm glad you come and viewed this and kind of got in on it. If your grade is below 70%, you need to have a window open in Buzz and be working on whichever assignment that you need to get caught up on. If you're behind, boy, this is a good week to kind of work hard and get caught up so you can enjoy next week, spring break, when we're not doing anything. There's no assignments. You may have to use that to catch up if you don't do it this week. So I'm encouraging you to get that out of the way so you can kick back and just enjoy the spring break, because we all need a break. We need a break. It's there for a reason. It's just time for a break. So if anyone has any questions, anything you're working on, please let me know. I'll turn the camera back on. We'll do some math together. But otherwise, just be working on what you need to work on. And I'm here when you have questions or needs.